we know how to find sine, cos, and tan of pi over 3, pi over 4, pi over 6, or any other angles in those families. And we also know how to find sine, cos, and tan of any of the axis angles, which are just multiples of pi over 2. We can also use our secondary trig ratios or trig functions and find those as they apply to these angles. And thus far, those are the only exact values that we've been able to find. But let's check something out. Let's simplify pi over 3 minus pi over 4. We're going to use our 6 subtraction skills. Of course, in order to do this, we'll have to make sure that there is a common denominator, which for 3 and 4 would probably be 12. So pi over 3 I'll write as 4 pi over 12. Pi over 4 is 3 pi over 12. Therefore, pi over 3 minus pi over 4 is pi over 12. And this is rather exciting for maybe just one reason. Maybe you've got a bunch of reasons. Obviously, you're excited at home. I'm excited over here. There's all sorts of reasons to be excited. Maybe we're excited for the same reason, maybe not. The thing is, we could apply something like, I don't know, tan or cosine or sine to something like this, and thus be able to find sine of pi over 12 because we have a difference identity that allows us to evaluate a difference of angles. That's what we're going to do right down below here after I finish erasing some stuff I got to erase. So we will evaluate sine of pi over 2. We will do it like so. Oh, sorry, not pi over 2, pi over 12. We're going to take sine of pi over 12 and we will express it instead as pi over 3 minus pi over 4. What we're going to do from there is use the fact that if we have sine of alpha minus beta, that we can express it as sine alpha cos beta minus, I'll check the formula sheet, pretty sure it's minus sine beta cos alpha. We're going to use that, but instead of alpha, we will have pi over 3. And instead of beta, we will have pi over 4. Because that's the case we're dealing with right over here. In that case, what this thing is equal to will be what we see over here, with all the alphas replaced by pi over 3s, with all the betas replaced by pi over 4s. So we rewrite it. Sine of pi over 3 minus pi over 4 is equal to sine of pi over 3 times cosine of pi over 4 minus sine of pi over 4 times cosine of pi over 3. This is a very crucial and critical step. I would say I've seen a lot of individuals kind of mess up around here. Maybe they try to take this sign and distribute it. But we've already noted that that is something we cannot do. We don't just distribute sine. We don't operate with functions like that. We do have to use the identities we are given. But from here, we can evaluate each of these values. We can evaluate sine of pi over 3. We can evaluate cos of pi over 4. We can evaluate sine of pi over 4. We can evaluate cos of pi over 3. If you're doing that with special triangles, go for it. If you're doing it some other way, go for that. Whatever you need to do to make sure you can actually get sine, cos, and tan for whatever angles we're playing with. 1, root 2, boom. I'm ready to go. So sine of pi over 3 is root 3 over 2. Cosine of pi over 4 is 1 over root 2. Minus sine of pi over 4 is 1 over root 2. And cosine of pi over 3 is 1 over 2. What we've got is a denominator that is 2 root 2 and a numerator that is 3 times 1, or sorry, root 3 times 1 minus 1 times 1. This is actually, according to the provincial standards as it has been marked in the past, okay as a final answer. For good form, we should of course just multiply top and bottom by root 2 over root 2. Sorry, multiply the whole fraction by root 2 over root 2, just so that we have a rationalized denominator. And our final result then will be root 6 minus root 2 over 2 times root 2 is 2 times 2, which is 4. It's worth noting that no matter what kind of pi over 12 we have for all these so-called k pi over 12 questions, our result will probably end up being some combo of root 6 and root 2 divided by 4. So it's pretty neat. See if you can get the exact value of the cosine of pi over 12 right over here. What would you have to do in order to actually get that value? Give it a try, give it a go, give it a shot, give it a stab, give it a whirl. Let's see what happens. Of course, you know me. I can't help but just jump in when I see math. So I'm going to evaluate cos of pi over 12 by expressing the pi over 12 as pi over 3 minus pi over 4. That's what I've found it to be. And then I will use the difference identity for cosine. What color did I do that in here? Oh, purple. Where we say that cosine of alpha minus beta is equal to, cosine used pluses. The coses were together, so cos alpha, cos beta is be plus. And then sine alpha, sine beta. So that's the rule we'll be using. We'll just replace all the alphas with pi over 3s and all the betas with pi over 4s. Oops, I did it again. So cosine of pi over 3 times cosine of pi over 4 plus sine of pi over 3 times sine of pi over 4. Our next step is again to evaluate these 4 components. You can use whatever method you need to do to evaluate those, just not a calculator. And we'll get values of them. Cos of pi over 3 is 1/2. Cos of pi over 4 is 1 over root 2. Sine of pi over 3 is root 3 over 2. And sine of pi over 4 is 1 over root 2. In our next step, we know that our denominator is 2 root 2. And our numerator, we've got 1 times 1 plus root 3 times 1, which is that. And for good form, let's just rationalize the denominator. And we'll end up with root 2 plus root 6 all over 4. It does look very similar to what we had up here. We've still got those same 3 kind of components, the root 2, the root 6, and the 4, but just combined in a different way. That's kind of worth noting. So again, all the final results will involve something like that. At least they will for sine and cosine. We might see different things end up for tan just because of the nature of good old tan. Any poops. we can use this kind of idea to find exact trig ratios for anything in the k pi over 12 family. So when we look at what is k pi over 12, like k would be some sort of integer, we're specifically talking about ones that don't reduce. So pi over 12 is one of them. We wouldn't really look at 2 pi over 12 because that's just pi over 6. We already know how to find sine, cos, and tan of pi over 6, so we don't need to worry about that. Similarly, 3 pi over 12 or 4 pi over 12, those also reduce. This one to pi over 4, this one to pi over 3. So we don't really worry about those as being in the pi over 12 family. The next one would actually be 5 pi over 12. And then 6 pi over 12 reduces. We could also look at 7 pi over 12. 8, 9, and 10 pi over 12 reduce. But 11 pi over 12 doesn't. 12 pi over 12, of course, reduces. That brings us up to pi, which is half of a whole revolution. So then we've also got 13 pi over 12. 14 pi over 12 will reduce, 15 pi over 12 will reduce, 16 pi over 12 will reduce as a fraction, so 17 pi over 12, 18 pi over 12 reduces, there's 19 pi over 12, 20, 21, and 22 pi over 12 all reduce as fractions, there's 23 pi over 12. So that's all the members of the k pi over 12 family from 0 to 2 pi that don't reduce. And we can get sine, cos, and tan, or even secant, cosecant, and cotangent for any of these angles if we can express any of those angles as a combo of angles that we do know exact values for. Funny thing is we can't. So we're going to use any other two angles in our special angle families to give us whatever combo we need to get that. One of those will always be something in the pi over 4 family, and then the other might be in the pi over 3 family or pi over 6 family. It is possible to do these with perhaps pi over 2 families as well, but you don't really worry about that as much. I would say always stick with something that involves pi over 4, and then probably looking at pi over 3, something in that family. But how would I actually go about figuring out what that is? Well, I want this to again be some sort of combo between pi over 3, pi over 4 maybe. I want to then break up the 7. And there's ways to break that up. Like in my head brain, I might think that, okay, we've got like 1 pi over 12 plus 6 pi over 12. That works. But I wouldn't really want that because this doesn't reduce into anything useful. So away with that option. Maybe I'm thinking to myself 2 pi over 12 and 5 pi over 12. Like sure, 2 pi over 12 reduces to pi over 6, but 5 pi over 12 doesn't reduce, so this isn't useful to me either. If I go through options, for me personally, the first one I see as useful for this is to express sine of 7 pi over 12 as the sine of 3 pi over 12 plus 4 pi over 12. And this is handy because 3 pi over 12 reduces and 4 pi over 12 reduces. They both reduce, so this is useful. You don't actually have to write it out as 3 pi over 12 and 4 pi over 12, but you will have to write it out as pi over 4 and pi over 3. And it's worth noting, this isn't the only combo that will work. You can even say that it's 9 pi over 12 minus 2 pi over 12. That works too. That will give you 7 pi over 12. You'll be using a difference formula in that case, but it will still work. So there are multiple ways to play with this whole thing. You will still get the same correct answer as long as your summation or your difference is correct here. So that will give you the same answer if you try that. I double dare you to finish this one off, and then once you've done that, try out the others as well. Your solution method might be different from mine, and that's okay. Just in that we might find different combos that give us the angle we want to work with. But try them out and see what you get, and then let's compare to what I put on this screen as well. All right, here I go. From the sum of sine thingies, I'm going to say, how does sine cos plus sine cos, that's what I need. So it's sine cosine plus sine cosine, but the angles swapped. Wait. I'm just realizing that sometimes my pi's look like 12s. I'm just going to rewrite them so they look beautiful. Lovely. Now we can evaluate each of those individually. Sine of pi over 4. Actually, if you rationalize in this step, then you don't have to rationalize later. So if you prefer to write sine of pi over 4 as root 2 over 2, go for it. That's that. Sine of pi over 3 is this, and cosine of pi over 4 is that. We've got 1 plus root 3 all over 2 root 2. And if we rationalize the denominator, we are looking at root 2 plus root 6 all over 4. So that is my answer to this one. Hopefully you're trying these. Try them all out. Oh my goodness, 17 pi over 12. There's a bunch of ways to get that. All right, you could say you've got 20 pi over 12 minus 3 pi over 12. That'll work. Or 15 pi over 12 plus 2 pi over 12. Maybe you went with that. That's okay too. It wasn't my choice. Like the first thing I saw was different. And I decided to express this as 8 pi over 12 plus 9 pi over 12. But it doesn't matter if you expressed it differently, as long as this certainly still gives you 17 pi over 12, and you still got cosine here, then you're still correct. All right, let's keep going. I'm going to reduce these fractions. 2 pi over 3 and 3 pi over 4. And honestly, I can't remember if I mentioned this earlier. You don't have to show this first step as long as this second step is correct. I just find it's useful to see this first step so you can identify just where your values are coming from. And it helps when you're going back to check your work, like, where did these values come from? Oh, right, they came from these ones. Anyways, cosine is cos minus sine. So cos of 2 pi over 3 times cos of 3 pi over 4 minus the sines of those angles. Sine of 2 pi over 3, sine of 3 pi over 4. And now I'll evaluate those four ratios. Cos of 2 pi over 3 will look like 1 over 2, but it will be negative. 3 pi over 4, cosine is negative for that as well. That's quadrant 2. And that's an over 4, so 1 over root 2. Sine of 2 pi over 3 is positive. Sine of 3 pi over 4 is also positive. Boom. What do I have here? So negative is positive 1 minus root 3 times 1. What? That's over 2 root 2. overall giving me an answer of 2 minus root 6 over 4. That one is done. So again, your steps might have been different if you chose something other than 2 pi over 3 and 3 pi over 4. But your end result should still be same. You might have it phrased as negative root 6 plus 2. That's, oh, not 2, but root 2. Sorry, so let me give that a quick edit. But still same, still equivalent. And then there's this last, whoa, hey, yo, that's not pi over 12 at all. What's going on? This is in degrees. And pi over 12 is equal to 15 degrees. So we're looking at a multiple of 15 degrees here. The concept is still the same. We want to find two angles in our magical families that can actually give us 105 degrees. So you'll have to play around with it a bit. Again, I think it would be helpful if one of them was in the pi over 4 family and then the other was something else. But follow your heart. We could go with 60 degrees plus 45 degrees. That works. You could go with 135 degrees minus 30 degrees. That works. Me, personally, I'm going to go with 150 degrees minus 45 degrees. This choice is irrelevant as long as it's a valid choice. This is a valid choice. So would the others. I'm going to go with it. Whoa, okay. So, according to the difference identity formula for tan, if I'm not mistaken, that gives us a subtraction on top. And on the bottom, it was 1 plus the product. So that's what I get there. Tan of 150 is related to a 30-degree angle. 1, 2, root 3. So tan of 150 will be negative. It's quadrant 2. That's negative 1 over root 3. Tan of 45 is just 1. That's all I really needed. Okay, 1 plus, and then tan of 150 is negative 1 over root 3. Tan of 45 is 1. I'm going to multiply top and bottom here by root 3 over root 3 because this is just a little complex. Anyways, this times root 3 is negative 1. This times root 3 is negative root 3. Well, on the bottom, 1 times root 3 is root 3. And 1 over root 3 times root 3 would be just 1. And to rationalize this, we'll have to multiply by the conjugate of that denominator. On top, I might consider doing some scrappy scrap work. Negative 1 minus root 3 times root 3 plus 1 will give me some value, which is, honestly, I would write this in a different order just because I'd prefer to see it like that. Any poops, we've got negative 3 minus, this is just the opposites of each other, irrelevant, minus root 3 minus root 3 minus 1. So we've got negative 4 minus 2 root 3. That's what I'll put on top here. So negative 4 minus 2 root 3 all over, and this multiplying by the conjugate would be 3 minus 1, so 2. And since all three of these have a common 2, we can just say we're at negative 4 minus, oops, not negative 4, silly dilly. Negative 2 minus root 3. So that simplifies pretty nicely. Boom, this is done. Boom. Done. There's quite a bit of practice. Whoop! There it is. It just says number 8. You know that's probably got like an A, B, C, D component to it. So it's a bit, but practice with these. It's a finite number of questions that can be asked for these kpi/12 questions. You've got sine, cosine, tangent, and secant, cosecant, and cotangent, and 8 possible angles that they can be asked of. So really there's only 48 distinct questions that could be asked. And maybe they could be asked in radians or degrees. But they all kind of work the same way. So practice them, give them a go, kind of get a feel for breaking a kpi/12 angle into other angles that we can work with. And of course, if you have questions, comments, concerns, you can always let me know. And I hope that you do. That's it, that's all. I will see you in the future. Tell everyone I say hello, and tell someone that you care about them. The end. Well, the 4th out of 5, I think, actually. It doesn't really matter. But it's almost the end. We just got the one section left, and it's just identities. Yeah, there it is. Whoop. Yeah, anyways, the sort of end. The end of this part. This part's over. This part's done. There's nothing more for this part. So let's stop this video. If you're listening, you're really cool, and you keep that up. The end. No, sorry, it's not the end. Gosh. The 80% way. That's it. Stop listening. It's over.